In this video, we're going to talk about fields. We're going to talk about the difference between static fields and instance fields. Unsurprisingly, it's quite similar to the difference between static methods and instance methods. We're going to talk about read-only fields. So let's just start by talking about local variables. Now, you remember that a local variable can be declared in two different ways. You can say var, and then the name of the variable, and then an equals, and then the initial value that you would like for that variable. And if you do that, then the compiler deduces what type you intended the local variable to be on the basis of the type of the initializer. Or you can be explicit about it, and you can say, instead of var, here's the type, here's the name of the variable, and then optionally you can say whether you want a value or not. You have to eventually provide a value before you read the variable, because C# requires that local variables be definitely assigned before they're used. So a field is a lot like a local variable. It's a named storage location. It's a variable. It stores a value. What's the difference? Local variables are associated with a particular activation of a method. So what I mean by that is when a method is called, if that method has parameters, those parameters suddenly spring into existence with the values of the arguments. If the method has local variables, those local variables suddenly spring into existence. When the method returns, those variables disappear. Right? So when the method is activated, the local variables appear. And they may disappear when the method disappears. A subject that we won't be covering in this course is there are some situations in which local variables do not disappear when a method returns, but we're not going to talk about that in this course. So what are fields? Well, instance fields are associated with an instance of the class, not with an invocation or an activation of a particular method. Right? Now, fields may not use the var syntax. This is a bit unfortunate. There are good technical reasons why it was difficult to do that, involving some complicated, strange looping scenarios where you can end up with fields whose initializers depend on other fields, and it gets quite complicated. I'm not going to go into the details, but suffice to say the C# compiler team made the wise decision to say that fields may not use the var syntax. Only local variables can use the var syntax. So let's take a look at some examples of some fields, and hopefully it'll become clear. I'm going to temporarily put our little Hangman project aside and give you some specific examples of how fields and properties and things like that work. All right, so here I've made a class called field example because I'm not very original. And as you can see, a field declaration looks exactly like a local variable declaration. I have the type, string. I have a name for the field, which we'll call name. I have an equal sign and an initializer. And so great, we have declared a variable of type string called name, but it's not in any method. It's just straight in the class. As I said, the var syntax is not supported. If we try, then we get an error message that says the contextual keyword var may only appear within a local variable declaration or in script code. And I'm not going to tell you what or in script code means because boy, is that complicated. Suffice to say that there has been for a long time a desire to have a more scripty version of C# that you could use in scenarios like scripting administration scripts, that kind of thing. Seems kind of odd that this error message calls out or in script code, but there you go. You don't really need to worry about that. All right. We can also have read-only fields. A read-only field is interesting. Fields are variables. Variables change. Variables vary. That's why they're called variables, as I often say. A read-only field is a variable in the constructor. So if field example has a constructor, then it may change the value of this field, or we can change it right here. We can say that this is equal to 123.45 m because it's a decimal. That's perfectly fine. But if we tried to change this field anywhere else other than in the initializer or a constructor, then it would say, sorry, that's only a variable within the constructor. Outside, it's a value. Its value cannot change. useful thing, read-only fields, because there are often properties, there's often data associated with a class where you would like to say, I would like this to be specified in the constructor, and then I don't intend to ever change it. And so please don't allow it to be changed. Now, the initializer here, you see I had an initializer here where I said, well, this name is equal to Eric initially. The initializer may not refer to other fields. So you see I've said this.name.length. And if we hover over this thing, it says keyword this is not available in the current context. And even if I take the this away, because it's optional, we're inside the class, now it will say a field initializer cannot reference the non-static field, method, or property name, right? Because that would implicitly require talking about this. This is yet another of my pet peeve error messages in C#. The C# compiler knows darn well that this thing is a field. So why does it say field, method, or property? Because whoever wrote that error message didn't want to write 3 error messages. All right, so why not? Why can't we reference this? And therefore, why can we not reference other fields in field initializers? And the reason is, I said earlier that C# allows you to reorder fields to your heart's content, or reorder anything in the class to your heart's content, with the small exception of static fields. And suppose that we decided that, due to some edit, that we wish to put this down here. Well, now, which runs first? Does this initializer run first? Or does this initializer run first? If this one runs first, then name.length is valid. If this one runs first, then name is null. Right? And this will dereference null. So in order to solve this problem, C# simply disallows it. Right? The other thing is when the field initializers run before the constructor runs. The constructor might do something that is necessary to initialize state that is necessary for some method to run. Right? So if we had a method in here, right, this.length is equal to this.whatever, right? The whatever method might rely on the constructor having run before it runs, but the constructor hasn't run at this point. So for both of these reasons, C# disallows you to do any access to this within an instance field initializer. All right. So far I've been talking about instance fields. There are also static fields. Now we know that static methods are methods that are associated with a particular class. They don't have a receiver, or rather the receiver in the code is the class itself. There's no this associated with a static method call, whereas an instance method has a this associated with the invocation. You don't ever invoke a method with a null receiver. That will crash, and so on. Static fields and instance fields are the same. The instance fields are associated with a particular instance of the class. That's why they're called instance fields. Static fields are associated with no instance of the class. They are associated with the class itself. Static, not really a good name. I think I've complained about this before. It really should have been shared. That's what it is in Visual Basic. Static fields are called static fields for historical reasons. The name comes out of the design of C and C++. So anyway, we have a static integer here called count. We're going to initialize it to 0. And it is associated with the class, not with any particular instance of the class. So let's actually debug through some code here and see what happens. Right? I've created a little main method here. All right, first thing I'm going to do is I'm going to call a method. I'm going to create an instance of the class, field example, and I'm going to pass some value into its constructor. So let's take a look at what happens. So I just tried to step into a constructor, but notice the first thing that happened was a field initializer ran. So control went directly to the field initializer, not to the constructor, to indicate the field initializers are going to run before the constructors do. All right, we can step through that. Now the constructor starts. All right, so we have a constructor. Its name is the same as the name of the class. It takes a parameter, some decimal number of dollars. All right, what are we going to do here? All right. we're going to write out this, not dollars, right, which is 123.45, but this dot dollars, which is 0. So notice what we just did there, right? We have a parameter called dollars, and we have a field called dollars. We just wrote out this dot dollars, right? But what would have happened if we had just written out dollars? Okay, let's restart this and see what happens. The value of dollars here is 123.45. The variable here is referring to this parameter. It is not referring to this dot dollars. Right? So there's a rule here. The rule is that this is optional, right, as we talked about before. But that rule is actually a bit subtle, because in a conflict between a local or parameter, right, and in this case this is a parameter, and a field, the local will win. So you kind of think about C# as trying to reason from the inside to the outside. And it says, well, this dollars here is very close to this one here. We only need to look inside the method to find this meaning of dollars. But we would need to look outside the method in order to find, or outside of the method but inside the class, in order to find this meaning of dollars. And therefore, the one that's closer wins. So this is something to be very aware of. It's quite common to have a parameter and a field of the same name, and it is super easy to get them confused. So if we want to refer to the field, always qualify it with this. Right? So in this case, we would say this dot dollars is equal to dollars. So the field takes on the value of the parameter. All right, so we see before it runs, this dot dollars is 0, dollars is 123.45. After it runs, this has become 123.45. Another thing you notice, and this is very subtle, you notice the this here is no longer written in that light font. Right? Visual Studio is now saying, oh, you know what? This one can't be removed without changing the meaning of the program, so don't do it. Right? Keep that one the way it is. Very subtle, but Visual Studio is good at these kind of subtle cues. All right, so what about that static field? We had a static field called count. It's currently 0. We could access it the way that any static is accessed, by giving it a receiver that is the name of the type. In this case, the name of the type is field example. But once again, you see Visual Studio has slightly lightened this thing, indicating that well, actually, that's not necessary. We could just access it using count. So any member, whether it's instance or static, can be accessed from an instance method without qualifying it with either this or qualifying it with the name of the type. All right, so let's increment the count. So count is now equal to count plus 1. So count is now 1. It was 0 before. Now, can we access static fields using this? That's an interesting question. If we try to, then we get an error here. It says member field example.count cannot be accessed with an instance reference. Qualify it with a type name instead. So this is not legal. You have to say field example.count or just plain count. You can't say this .count, because that makes it look like this is an instance member when in fact it's a static member. All right, so coming back into our main method here, a few more interesting things about fields. Fields cannot be accessed by default from outside the class. So for example, here we have our instance of example. It's got a field called name. It's got a static field called count. We can access neither of these from outside. Right? This says inaccessible due to its protection level. That also says inaccessible due to its protection level. We will talk about what protection level and accessible and all of those things mean in a future video. Fields are almost always made inaccessible. This is part of the sort of encapsulation, information hiding strategy of object-oriented programming. Fields are usually implementation details. Properties are usually sort of public surface area details. So if you want something to be published, then you to another team so that they can use it, then you would use a property. If you wanted something to be a private implementation detail, then you would use a field. I want to talk a bit more about how the static and instance properties differ, just in case that's not clear. So let me step through this program again, and we'll create a second instance of the field example class. All right, so when we create our first example here, we initialize a bunch of stuff. Count started off as 0. Now it's 1. Now we'll create another one of them. Right? So we'll step into in the first one, we said that the dollar amount was going to be 123.45. Now we'll create a second one. Again, we save away the value into the field. And again, we increment the count. And the count was 1 before. And so now after the increment, it's 2. All right, so let's take a look at these. We have our first one. Right? Its dollars field is 123.45. This is an instance field. The instance field is associated with a specific instance of the class, right? This instance of the class. This is a completely different instance. We created it with a new expression, an object creation expression. And therefore, this guy has a completely different value for the field. Right. Now, if we look at the static members, right, the count is 2. We created 2 objects. Every time we created an object, we incremented count by 1. It started off as 0. So this field is shared amongst all of the instances. This isn't associated with any particular instance. It's associated with the class itself. Now, you notice that the code that I tried to write up here could not access those private implementation detail fields. The debugger can. We are running the debugger here, and we have no problem looking at this thing and saying, oh, well, it's got a field called dollars and a field called name and a static field called count. Right? The debugger is magical. The debugger has complete access to everything. It has full knowledge about the entire program. So we don't have to worry about, well, this is not accessible, this is accessible, and so on. The debugger can see everything. And as you can imagine, it would be quite difficult to debug programs if it couldn't. All right, I want to switch gears a little bit here and talk about a special kind of field called constant fields. Constant fields are not variables. They must be initialized. The initialization must itself also be entirely constant. And constant fields are automatically static. So let me give you an example of that. Right? We could, up here, we could say public constant int my constant is equal to 123. Sorry, public const int my constant is equal to 123. All right, and now down here, we could say console.writeLine field example my constant. All right, so this is an example of a constant that's accessible from outside the class. There are many other constants that are accessible from outside their classes. For example, the system.math class has a constant called pi. It's a constant double, and you can see that its value there is exactly what you would expect. Something a little bit odd and subtle here is you notice that the pi here is written capital P, capital I. That was actually a mistake that was made very, very early on in the design of .NET. The intention was to have all of the constants use this convention, right? The standard convention in C# of capital letters followed by small letters, capitalizing every word along the way, which is often called Pascal case. The intention was to do this as pi like that, but somehow that got to be pi with 2 capital letters. Don't use the all caps convention for constants. Java does that, and some other languages do that, but it looks weird in C#, so don't do it. We've seen constants, and constants can't be changed at all. They're not variables. We've seen read-only fields. Read-only fields can only be changed in the constructor. So why would you use constants versus read-only fields? The differences are, first of all, constants should be things that are the same for all time. Right? The value of pi is never going to change. A read-only field could be something like a version number, right? The version number is not going to change while the program is running, but the version number might change in the future, right? And therefore, it should not be a constant. Constants should be things that never, ever change, right? Like the number of protons in an atom of gold is never going to change. Gold is defined by that, right? So that would be a good example of a constant. Whereas something like the name of your bank or the exchange rate of dollars and yen, that should not be constant. It might be sensible to model those things as read-only, or it might not, but they're certainly not constants. The other reason to choose constants versus read-only fields is any field may be made read-only. A constant field must be a string or a numeric type, or an enumerated type. You can't have constant fields of other types unless they're null, which is pretty useless. All right, summing up. Fields are kind of like local variables, but they are associated with an instance, if they're instance fields, or they're associated with the type itself, if they are static fields, rather than being associated with an invocation of a method activation, the way local variables are. Constant fields are not variables. The value has to be known at compile time, and once a constant is set, you should treat it as being set forever. Read-only fields are kind of halfway between, right? They are variables as long as the constructor is running or a field initializer is running, but they are treated as though they were values in all other contexts.